Welcome to the pre-recording of lecture 20 of MCS 481. So this lecture is scheduled for the end of week 7, and we are about smack in the middle of the course, starting the very important topic of the Voronoi diagram. So there will be 3 lectures on Voronoi diagrams. Today we will define what is a Voronoi diagram, what are the basic properties, and we will prove statements on the complexity. In particular, that the Voronoi diagram for n points has a linear complexity, linear in the number of points. And that will enable, that we will see next time, that will make possible an n log n algorithm. Okay, what is a Voronoi diagram? Well, imagine the following problem. We have 3 post offices and they are located symmetrically here, represented by the black dots. The region we consider is the square, and we have partitioned the entire region in three subregions. The meaning of the subregion is that people in the green region go to the post office that is closest, and that is marked by this black dot. So all points in regions of the same color go to the same post office, assuming that naturally you would go to your closest post office. So the post office problem of locating the nearest post office to you for every point in the square is solved by this partition. So we have the green, the red, and the blue, and then we have the white lines. If you live on a white line, then you have choice. If you live right in the middle here, where this white line meets, then any of the 3 post offices is just as close as any other. So you have choice. So what this slide shows is a Voronoi diagram for 3 points. That's it. So we're going to discover this for general point configurations. This is a mathematical computer science course. So the computer science aspect is that we consider, well, the practical computer science aspects is that we consider software. We have seen Seagull throughout this course, but here you see the code to compute and draw the Voronoi diagram for 10 random points. And this consists of 7 lines of Python code, which will work if you have numpy, scipy, and matplotlib installed. So these are the most basic packages in the Python ecosystem. So here is then a diagram for 10 random points. So the random points are marked in blue. We have the lines, so these were the white lines, that are the edges of what we will call the Voronoi cells. In orange are the vertices of the Voronoi cells. So, and there is not only a script, but there is also a Jupyter notebook, so I probably should execute this. And you see, whenever I'm executing this, I have another example of a Voronoi diagram. Let me do this again. So here you see another example of a Voronoi diagram. looking at many examples is good introduction, is good practice. You get a nice picture to look at, and that gives you an idea of what is a Voronoi diagram. There is much more, and here actually I was not that careful, but I started dumping the code of a script in this code cell. So we have the vertices of the Voronoi diagram. There are what they call the ridge points and the ridge vertices, and there are the cells. So you see the random points, the vertices. Actually, the vertices of the Voronoi diagram are the computed. So these were the oranges, the orange dots. Here you see the definition of the vertices and then the cells as well. So we have 10 points in our entire Voronoi diagram, the 10 sites. Okay, so for now, the remaining of the code in so which I just flashed and scrolled through, maybe later will be important later on if we are examining the particular properties of Voronoi diagrams. So this Jupyter notebook and the Python code uh, gives us a very quick way to compute and analyze many examples of Voronoi diagrams. Okay, so in some sense I mentioned this is a mathematical course, fine looking at pictures, it gives us some intuition, but we need a definition. We need to rigorous define the concept of a Voronoi diagram. So here it is. So we are using the classical distance between two points, also called the Euclidean distance. So here defined by this formula, which involves the square root of the sum of the squares of the distances between the coordinates of the point. Then what is a Voronoi diagram? Well, a Voronoi diagram is a collection of Voronoi cells. And a Voronoi cell is computed from the input. So we have given endpoints in the plane. For each point in the input, we compute the collection of points, so the Voronoi cells that are closest to that point. So here you see the definition of a Voronoi cell. It consists of all points that are closest to the current point Pi than any other point in that set, in that input set. Then the Voronoi diagram is simply the collection, the set of all the Voronoi cells. Good. How do we compute this? Well, we saw an example very early on with the post office problem. If you have a triangle, or even if we look at, say, 2 points, then actually the Voronoi diagram is defined by the bisector. So the Voronoi cells, they can be finite, but they can also be infinite. So here we have two half planes. Two half planes defined by the bisector. So here, how do we define this? So we have the half plane for all the points closest to P, and the half plane of all points closest to Q. So these are the halves. So the bisector splits the plane in half. So if you have 2 points in the plane, then the bisector essentially characterizes the Voronoi diagram. So the Voronoi diagram of 1 point, if you like, is the entire plane. Okay, so here the notation. So the notation of h p comma q, it implies the distance. So if r is in the half plane p comma q, then the distance to p is less than the distance to q. Okay, so in some sense, if you like, this is a sharp inequality. So the Voronoi diagram consists of the bisector and the two half planes. So the bisector is the line where all points are at the same distance. So that's an alternative definition of the bisector. Okay, so this is a Voronoi diagram for 2 points. Here is the consequence of the half planes. And also in some sense, if you have few points, you just draw all your bisectors. So here I drew all the bisectors for P1 with respect to the 4 other points. So the characterization of the Voronoi diagram, Voronoi cell for P1, the first point, is actually defined by the intersection of the half planes. So this intersection is shaded here in green. So I also actually have the Voronoi cell for P5 in this way. Or not really. So I have not sufficiently many bisectors. So I would need to draw also the bisector that separates P4 and P5. But you see, computing one Voronoi diagram consists of computing all the bisectors and then intersecting all the half planes. And earlier in this course, we have seen, or actually quite early in the beginning, that every half plane is convex and the intersection of convex sets is again convex. So the fact that Voronoi cells are convex follows from the property that the intersection of convex sets is again convex. And convex sets are very nice to work with. All right. Here are some other cases. What if all your points are collinear? When do you have this? Well, if you look at the subway, all the stations are lined up. Where is your closest subway stop? If all the points are collinear, then the Voronoi diagram is defined by n-1 parallel lines. Otherwise, so if the points are not collinear, then all the edges are either line segments or half lines. So this is important here. We only have parallel lines, entire lines, when we have 3 points that are collinear, when we have collinear points. If all the points are sufficiently generic, so no 3 points lie on a line, then we have either line segments, so they can stretch out to infinity, or we half lines, they stretch out to infinity. Line segments are bounded. We defined a Voronoi diagram as a collection, but all the edges are connected. So earlier in the course, we saw the half-edge data structure to represent polygons. So the fact that all the edges in the Voronoi diagram for generic point configurations are connected, this data structure will also be suitable here. Okay, so this is a mathematics course, so we cannot leave the statement of a theorem unproven. So in some sense, this theorem is important because it represents another example of a Voronoi diagram. If you like, somewhere a degenerate example, kind of a non-generic, not a configuration that is regular. But it also says something about properties of Voronoi diagrams. What are the boundaries of the cells? So every Voronoi cell is then either bounded by a line segment or a half line. And there is the connectivity, which will then also be exploited when we get to algorithms. Okay, so let's prove this statement. So assume first that we want to prove that all the points are not collinear, so no 3 points are lying on the line. Then we need that all the edges are either line segments or half lines. So assume that we have a full line. So we have a bisector, if you like. So the edge L is actually now separating PI from PJ, and it is a full line. Then consider a third point. By the assumption, so the points are not collinear, but we're proving is the other way around. We actually have a half line. Then actually we can only have the full lines when PK is collinear. So assume that it is not. Okay, so what do we have then? We have that the bisector of PK with PI is actually not parallel to the bisector, and then also it's not parallel to the bisector of PK with PJ. Okay, so either does the line has then to belong to these half planes. So the half planes that is going to define the Voronoi cell for PK. So either L has to lie then in these half planes. And this cannot happen if the bisector is a full line. So, okay, that's that. Okay, so we have to prove the connectivity. So all edges are connected. Again, by contradiction, assume that they are not connected. Then actually we have a cell that splits the entire plane in two. But this can only happen if the Voronoi cell is bounded by two parallel lines. But we can only have two parallel lines if the points are collinear. So the assumption that the edges of the Voronoi diagram are not connected can only happen if you have a Voronoi cell splitting the plane in two, or alternatively, if the bounds of the Voronoi cell are two entire lines and they will be in parallel. But that can only happen via the previous slide that we just proven, that if the points are collinear. So this violates the assumption that we made. So all the edges are connected. So this is an important property of Voronoi cells and Voronoi diagrams for points that are not all on a line. So regular generic point configurations. Okay, so here is a first algorithm by computing all the bisectors. So we have 5 points. You can also use the software to verify your answer. But in some sense, well, you can also write some simple code to simply list all the bisectors. If you feel a tickle, you feel the programmer in you the urge to write some code. Well, if you write some code, then you will immediately see that this is a quadratic algorithm. So you have to list all the bisectors. In the algorithm, in step 2, you have to throw out certain bisectors or shorten some lines. A bisector is a full line, but this point configuration is not collinear. So you have to list all the edges and the vertices. So for part one, you could use the Python code for that. And then describe how the algorithm, if you had to do this by hand, and 5 points, it's not that hard. Quadratic time is not that hard here. So this could be an exercise entirely paper and pencil. The exercise is important, so I list the exercises smack in the middle of the lecture that it is intended for you to pause a little bit. And the important question is here, we have an algorithm. It's simple to execute, but it is quadratic in the number of points. So that's the cost. The question that we're going to answer actually in this lecture now is that sharp. So if the complexity of a Voronoi diagram is indeed n square, then actually the algorithm that is suggested here is a good enough algorithm. Okay, so complexity. So how many edges or vertices can a Voronoi diagram have, or one Voronoi cell? So here is a Voronoi diagram, another example, extremely regular. So we have 8 points, and the red point also on a circle, and with the center we have the red dot. In green, so we focus on the green Voronoi cell, which is an octagon. So the octagon has 8 edges and 8 vertices. So for 9 points, we do have a Voronoi cell with 8 vertices and 8 edges. So this is one Voronoi cell, and we have as many Voronoi cells as we have points. So can we have a situation like this, so that every Voronoi cell has n minus 1 vertices and n minus 1 edges? Here obviously not. So the other Voronoi cells, they all have a much nicer complexity. Only 2 vertices and a vertex at infinity, 2 half-lines and 1 line segments. So all the other Voronoi cells are a lot nicer, smaller. And you can escalate this. So instead of having an octagon, you can have a 64 gon, and whatever number you want. So you see that this is kind of an alarming example. So the question is here, can we ever have a Voronoi, so the total number of vertices, the total number of edges? What can that be? Can that be quadratic? Um, Another exercise here. So this is an exercise that invites you, that probably should be done, so there are many more points. It's okay to do this by hand as an exercise one, but here actually you would need to, let me see how many points there are. There are 9 points, and it may very well have been that I took the coordinates in the picture. So so I was using Tixi, but the exercise here asks you to use preferably the scipy package, the wrapping of QHull. And what you would need to do is actually arrange for the count. So count the number of vertices, count the number of edges. Okay, again, slow down, see for yourself or compute for yourself. So the software, so you could actually, I mentioned the 64 gon. Computers are very fast, and there is no limitation, there's no restriction why you wouldn't define all your points on a circle and then an extra point with the center, and see what the total number of vertices and edges is. You can also run the notebook over and over and over again, and each time report the number of vertices and the number of edges. So if you are more a statistician, you can compute 1000 Voronoi diagrams and make a histogram on the number of vertices and the number of edges. So exercise 2 is again a slow down, inviting you to experiment and to compute a little bit. Because the main result follows here on the complexity of a Voronoi diagram. So for endpoints, at least 3, the number of vertices is at most 2n minus 5. The number of edges is at most 3n minus 6. So we have very precise bounds. So let's look at the collinear. Um, so we tend to think about generic situations, but let's look at a collinear set. Then actually the edges are the parallel lines n minus 1, and we have only one vertex here. So in some sense the complexity of a Voronoi diagram for a collinear set is um, quite simple. So these are bounds. Are they sharp? That's another question. If you do your statistical runs, then you may find something like that. But let's look at the theorem that we will be using to prove this. So we have Euler's formula coming from graph theory. So we have seen it earlier. If you are actually want to be self-contained as well, then look at the proof of Euler's formula. But we will prove the bounds on the number of edges using Euler's formula. Okay, so number of faces, so these are the cells. For every cell, um, there is one site. I should say the input points are called sites. There might be confusion with convex hulls, the problem we started with in this course. Then some points may also be vertices. That is not the case here. So that's why the vertices are the intersections of the edges, but the input points are called the sites. So the n sub f is actually n, and that's the number of points. Good. Now what about the number of edges then? So every edge has 2 vertices, and the degree of every vertex, so the number of edges that come in there, is at least 3. So you can bound twice the number of edges by 3 times the number of vertices plus 1. Why the plus 1? Because we always have the vertex at infinity. So all the half lines that go off to infinity, they all connect to the same point at infinity. So you can kind of see if we are living on a ball on planet Earth, and we actually, our current location, you could imagine the point if you build a tunnel straight to the Earth, then you come out there, and that's your point at infinity. So all the half lines, they connect to there. So that's the topology. Okay, so we have n, we have the number of edges, the number of vertices. So we apply Euler's formula, and we eliminate the number of edges. Also, we write again n of f is actually n. So, and then actually we can bound, so via these inequalities, we can bound the number of vertices as 2n minus 5. So this is plainly working with these inequalities. So the first result, the number of vertices, this follows from Euler's formula and the observation that every edge has two vertices and the degree of each vertex is at least 3. So this gives the bound on twice the number of edges. And then we do some calculations with the inequalities and we find the bound on the number of vertices. So I'm half an hour in and I have shown with the aid of Euler's formula, which you should have seen in graph theory, with the aid of Euler's formula, we have our first important result. Now the second part comes then again with Euler's formula, and now we are trying to find a bound for the number of edges. So we look at the same inequality again. So every edge has every vertex. So a vertex, again, you can think of it's an equality if everything is again in general position. If there are not more than 3 edges coming in and to a vertex, then we have this inequality again, and we now see it from the other side. So we have the bound on the number of faces again. We are eliminating the number of edges from this. So we are replacing, so again, the number of faces, and then again, Euler's formula. So I was a little bit confused here, but perhaps let me emphasize this. So we have Euler's formula rewritten here, and this is what we apply. So this is this inequality here, but where we have replaced n of f is n, and then we have this bound here. So these are the replacements. Okay. All right. And this gives us then the second part of the result. The number of edges is bounded by 3 times n minus 6. Quod erat demonstrandum. So this is the main theoretical result. So as mathematicians, this makes us quite good. It also has important practical implications because now we can look for algorithms that are n log n time. We will find such, which will describe and define such algorithm in the next lecture. Okay, so here it is. Collinear points, if you would use the straightforward algorithm, computing all the bisectors, then you actually have a quadratic cost algorithm, quadratic in the number of sites. However, the Voronoi diagram does not store all the bisectors. It's consisting of vertices and edges. And we have just shown that the number of vertices and the number of edges is bounded by linear formulas. So the number of vertices can be at most be the double, not even the double of the number of sides. And the number of edges can be almost the triple of the number of sides. Therefore, the big conclusion is that the complexity of a Voronoi diagram is linear in the number of sites. So in the previous lecture, we did some probabilistic analysis. So we talked about averages. Also, you can experiment with thousands of Voronoi diagrams and compute the average number. So exercise 3, you can solve experimentally. So run thousands of experiments and report the number of vertices of a Voronoi diagram. So this is useful to see how sharp these bounds are. I got this from a modification from the exercises from the textbook. You can also, according to the textbook, you can, as a consequence, you can find a constant for the average number. It is average because we have seen that a Voronoi self of n sides can have n minus 1 vertices. So, um, and actually that is, so you should still define this, I'm sorry, divide this by n for the average number. So that actually was a good configuration. All right, if you look into the textbook and the exercises, you will find a number, the average number. Either you solve this exercise by reasoning on the statement. So you might be inclined to divide by n when you take an average. You also have the total number of vertices. What does that say for the number, the average number of vertices for endpoints? Okay, I will end with some characterizations. So these characterizations are important for the next lecture for the algorithms. So we will see also a sweep line algorithm. We will call it the beach line algorithm. Um, Here is the notion of the largest empty circle. So if you have 3 points in the plane, then there is a unique circle that goes through it. So here you see that the center of this circle is defined by the intersection of the bisectors. So for this example here, we have two circles, P1, P2, P3, and it goes through the bisectors of these 3 points. So 3 points form a triangle, they're not collinear. So their bisectors intersect in a unique point, and you can draw the circle. So then in that point, so remember the post office problem. So there is a unique point where you are at the same distance of all the points. Well, that is the center. And you compute the radius by the distance to any of these 3 points. This is called the largest empty circle. So this actually, you can run around in this disk defined by the circle and not hitting any of the sides. So this is the largest empty circle with respect to this set of sides. Here you see another property of circles. If you consider 2 points, then you can draw a circle through these 2 points. Actually, you can draw more than one, but the circle that you draw has its center on the bisector. So, and the edge actually lies at the cuts this disk, if you like, the disk defined by this circle. It cuts this disk in half. So this is a diagonal. All right. This is important. I should have started with this. If you look at the bisectors again, which bisectors define the edges? Which bisectors actually define the vertices? Well, here you can see for 3 points on the largest empty circle, their bisectors define the vertices. So this is a characterization of the vertices. So this picture here characterizes the vertex of every point in the Voronoi diagram as the center of the largest empty circle. The edges are defined as the diagonals of the line segments on the bisectors. And again, they can be defined in relation with this largest empty circle. All right, characterization of vertices and edges. So what I said, and here are the pictures again. So um, this is so there is the definition of the largest empty circle, and then the observations that we made. The observations are here formalized in the theorem. So the proof of this theorem is actually clearly and systematically writing down the observations that I made on the previous slide. So if we have a vertex of a Voronoi diagram, then the largest empty circle contains 3 or more points of the Voronoi diagram on its boundary. Again, so this seems like an interesting thing to know. Who cares? But we will use these things when we get to the construction of Voronoi diagrams. So if we have an edge, then actually the edge is on the bisector um, between uh, these 2 points. And then also there is the connection with the largest empty circle. And the largest empty circle, the center is on this edge. So Q is on the edge. So the largest empty circle has only Pi and Pj on the boundary. All right. So the pictures show it, so you see it, and you can draw many, many pictures, or you can have the software generate many, many pictures. So here is where if you want to develop your skills with matplotlib any further, you can actually make drawings automatically. So you could superimpose, if you like, on the Voronoi diagram the drawing of all these circles that are centered at the vertices, and also compute the other centers. So this would make for very nice pictures. If you are a mathematician, then you must see the proof, and we go through the proof. Okay, so the theorem is implied by 2 lemmas. So if we have a vertex, then the largest empty circle contains 3 or more points. So if it is a vertex, then at least 3 sides. It's part of the 3 of the Voronoi cells of 3 sides. So this actually implies that it lies at the same distance. And it will be, if you draw the circle, it will be an empty circle, but there is no other side closer than these 3. Otherwise, it would contradict the assumption that we have these 3 sides. It would have meant that so if there was a PL, another side, then the PL would be, the L would have been the I, the J, or the K. 3 points uniquely define the circle. Okay, so there is an if and only if. So if you have an empty circle that have 3 or more points, then the 3 bisectors, they all have to pass through that point. And that actually implies that the center of this largest empty circle must be a vertex. So in a way, the proofs are actually you rewriting a restatement of the statement of the lemma. If you like, the lemma is actually a very short formal notation. Okay, and I didn't write QED, so we are at the next lemma. The next lemma is also an if and only if, but we break it up into 2 parts. So we have, if you have an edge of a Voronoi diagram, then it must be on the bisector. And on that edge, there is actually the center of the largest empty circle. So I just said it. So if you have an edge, then it must lie on the bisector. Every point on the bisector is equidistant. So if you take the midpoint of the edge and construct the circle with radius to distance from that midpoint, Q as the center, then that gives a circle that contains no other point other than the 2 points pi and pj on the boundary. And the statement of the lemma follows. So in some sense, the proof here is a little bit slower, spelling out what it means to be an edge of a Voronoi diagram. In the other way, if we have an edge on the bisector, and if we have a largest empty circle with a point on the edge, then that edge actually must be an edge of the Voronoi diagram. Okay, what is the property on the bisector? Well, if you are on the bisector, then you are at the same distance, and no other point is actually closer. So actually, it's a vertex. It's either it could be a vertex as well, but it lies on an edge. So assume now that we have actually an edge, so it's actually not a vertex because we would need 3 points and we only have 2. So therefore, that point lies on an edge defined by the bisector. Great. So I was thinking I had a lot of material. So we have formally defined what is a Voronoi diagram. We covered section 7.1. So the exercises were kind of critical to slowing us down to compute more examples. What actually we should also do is look at the manual of Seagull. So you see Voronoi diagrams have their own section in the documentation in the package overview. But what you also notice is that it's not just a plain pure Voronoi diagram, because if you think about the post office problem, that might have seemed purely ridiculous. I mean, they don't build post offices in the open field. Typically, they are in cities with roads. So you can kind of see here the map overlay problems are actually important. So there is also the dual of a Voronoi diagram. So in some sense, we started out with scipy, which is in some sense extremely great because we haven't come yet at the Loney triangulation. We will later cover that the Loney triangulations are the dual of the Voronoi diagrams. So in some sense, looking at, so I want to indicate that Voronoi diagrams figure very prominently in Seagull, but at the same time they are connected with a whole set of other tools. So that's why the scipy introduction via the spatial package is probably for this lecture the most convenient way of looking at it. Okay, I mentioned an exercise in the textbook. So exercise 3 is actually mirrored from exercise 2, I guess, or from the textbook. So also consider those exercises. So we have arrived at an important part in this course. So we are now at chapter 7, at the end of week 7. We will cover the first 10 chapters very carefully of the textbook, but there are 14 chapters in total that we consider. So in some sense, it's still the middle of the course, the middle of the semester. In the next lecture, we will define an algorithm, an n-log-n algorithm, as we will later then see, to very efficiently compute a Voronoi diagram. So Voronoi diagrams can be computed in n-log-n. It's just the same as sorting numbers. But our numbers are actually not numbers, they are points. So they are tuples.